In this video, I'm going to show you how to approximate the roots of a number using local linearity. So here we want to find the linear approximation, L of x, for the function f of x equals root x at the point x equals 25. And then we're going to use this linear approximation, L of x, to approximate the values of square root of 23 and square root of 29. Now remember, the linear approximation of a function at a point is just the equation of the tangent line at that point. And the motivation behind it is that we can use it to approximate the function's values near that point. This is especially useful for values which are difficult to compute, like we have here, square root of 23 and square root of 29. Alright, so first of all, remember the general formula for the linearization of a function at a point, x equals a, that's given by L of x equals f of a plus f prime of a times x minus a. Here the point in question has x equals 25, so 25 is our value of a. Let's go ahead and write that in. So L of x equals f of 25 plus f prime of 25 times x minus 25. Now let's go ahead and plug in for f of 25 and f prime of 25. We'll just work that out on the sides, starting with f of 25. So f of 25, using the definition of f, that's just square root of 25, which is 5. And then f prime of 25, that's just the derivative of f evaluated at x equals 25. So we have to compute the derivative. Let's start by just writing f of x. F of x equals square root of x. And we're going to want to use the power rule to differentiate this. So let's go ahead and write this as an exponent x to the power of 1/2. Then using the power rule, f prime of x we get by just bringing that exponent down. So 1/2. X, decreasing that exponent by 1, a half minus 1 is negative 1/2. And we can simplify that to just 1 over 2 times the square root of x. So plugging in 25 then, we have f prime of 25 is equal to 1 over 2 times the square root of 25, which is equal to 1 over 2 times 5, which is equal to 1 over 10, and we can go ahead and plug that in here. So let's go ahead and do this. L of x is equal to f of 25, which is 5, then plus f prime of 25, which is 1/10, times x minus 25. Alright, so that is the first part of the problem. We have our linear approximation, L of x. And now we want to work on the second part. We want to use L of x to approximate the values of root 23 and root 29. First of all, let's think about the square root of 23. So the square root of 23, that's equal to f of 23, because f is just the square root function. And f of 23 can be approximated using our linear approximation for f of x around the point x equals 25, because 23 is somewhat close to 25. So f of 23 is approximately equal to L of 23. And plugging in for L of 23, we just go ahead and plug that into our function up here. So that's 5 plus 1/10 times 23 minus 25. And now we just evaluate. So this is approximately 5 plus 1/10 times -2. Why don't we go ahead and convert this to decimal? So 5 plus 1/10 times -2, 1/10 times -2, well that's just minus 0.2. And 5 minus 0.2 is just 4.8. So here we have our approximation. Square root of 23 is approximately 4.8. And that makes a lot of sense because it's a little bit below 5, and square root of 25 is 5, so square root of 23 should be just a little bit lower. Alright, so there is our approximation for root 23, and for root 29, it's really just the same idea. Root 29 is equal to f of 29, which is approximately equal to the linear approximation L of 29. So we just go ahead and plug in 29 into L, and we get 5 plus 1/10 times 29 minus 25, which is 5 plus 1/10 of 29 minus 25 is 4. So 5 plus 4/10, which is 0.4. 5 plus 0.4 is just equal to 5.4. So there we go. Root 29 is approximately equal to 5.4. Okay, well that's cool. We can approximate the values of square roots using linear approximation. But you might wonder, how good are these approximations? Well, let's see. Rounded to 3 decimal places, the exact value of root 23 is 4.796, and the exact value of root 29, rounded to 3 decimal places, is 5.385. So we can see that, wow, our linear approximations are actually really good. Root 29 rounded to the nearest tenth is indeed 5.4, and same with root 23, rounded to the nearest tenth, that's 4.8, actually rounded to the nearest hundredth too. That's 4.80, and that coincides with our linear approximation. So wow, our approximations are impressively good. But just keep in mind that the further we get from our center of approximation, in this case that was 25, the less accurate the approximations become. So this linear approximation here can only be used to approximate square roots where the inputs are fairly close to 25. If you try to approximate the square root of, say, 1,000, with this linear approximation, you're probably going to get an answer that doesn't match up too well with the actual value. But nevertheless, linear approximations are really cool. So just keep that in mind as you do more of these problems. Alright, here's our next problem. We want to use linear approximation to estimate the value of the cube root of 8.6. So cube root of 8.6, that's difficult to compute because it's not a perfect cube. So the idea is that we'll use a linear approximation centered at the nearest perfect cube to make this problem easier. So let's think, what is the nearest perfect cube to 8.6? Well, it's just 8. We have that the cube root of 8 is equal to 2. So we're going to use a linear approximation centered at a equals 8. Now let's write down, what is that linear approximation? Well, again, remember the formula for linear approximation of f at a point A. Linear approximation is equal to f of a plus f prime of a times x minus a. So we know what our a value is. A is just going to be 8 here. But what about our function? Well, the function is just the operation that we're doing to the input. And in this case, that's just a cube root. So we have that f of x is equal to the cube root of x. All right, so let's go ahead and plug in this information. First of all, plug in a. So f of a is just 8, so f of 8, then plus f prime of 8 times x minus 8. Now we need to find f of 8 and f prime of 8. Well, f of 8 is easy. That's just our center here. We have that f of 8 is equal to the cube root of 8, which is equal to 2. So f of 8, this here is just 2. Okay, so what about f prime of 8? Well, we need to differentiate our function f here, and to do that, let's go ahead and express this as an exponent of x. This is x to the power of 1/3. That way we can use the power rule. So f prime of x, just bring down that power 1/3, and then decrease the power by 1. 1/3 minus 1 is negative 2/3. So simplifying, we have that f prime of x equals 1 over 3 times x to the 2/3, which is 3 times x to the 2/3. Then we plug in 8, so f prime of 8 equals 1 over 3 times 8 to the 2/3. And what's 8 to the 2/3? Let's just go ahead and do the denominator of that power first. What's 8 to the 1/3? 8 to the 1/3 is just the cube root of 8, so this is 3 times the cube root of 8, which is 2 to the power of 2. That's the remaining numerator in the exponent. 1 over 3 times 2 squared, well that's just 1 over 3 times 4, which is 1 over 12. So f prime of 8 is equal to 1/12, and we can just go ahead and put that up here for f prime of 8. So plus 1/12 times x minus 8. So that's our linear approximation for any general point x. And now we want to use our linear approximation to estimate the value of this root here, the cube root of 8.6. Well, the cube root of 8.6 is just equal to f of 8.6. F is just the cube root function, and f of 8.6 is approximately equal to the linear approximation, L of 8.6, because 8.6 is pretty close to 8. So we just go ahead and plug in 8.6 into our linear approximation. So this is 2 plus 1/12 times 8.6 minus 8. So this is 2 plus, well, 8.6 minus 8 is just 0.6, so 0.6, that's over 12. We can simplify this fraction, 0.6 over 12, so this is approximately 2 plus, just divide top and bottom by 6, you get 0.1 over 2, and half of 0.1 is just 0.05, so 2 plus 0.05, so 2.05 is approximately the value of cube root of 8.6. And that makes sense because it's a little bit over 2, and 2 cubed makes 8. Yeah, that's all checking out. So there's our linear approximation, and again you might wonder, how good is this approximation? Well, rounded to 3 decimal places, we have that the cube root of 8.6 is actually equal to 2.049. So that means our linear approximation is really close. It's accurate to 2 decimal places. And we were able to figure that out without even using a calculator. Alright, so now we know how to approximate the roots of a number using local linearity. And in the future, we'll also learn how to approximate the roots of a trigonometric function using local linearity.